Welcome back to Series on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we're going to cover another series test called the ratio test. And we're first going to go over the theory, and then we're actually going to do an example of this. Alright, so if you polled a bunch of calculus students after they completed the series exam, and you ask them which one of these tests would you probably have wanted to see more of on the exam, most people would probably say this test, the ratio test, and the root test from the next video. And that's because these tests are generally the simplest, I think. I think they're fairly straightforward tests as long as you know what you're doing. Most of it is just some pretty easy simplification algebraically. Alright, so when do you use the ratio test? So, if I have a series from n equals 1 to infinity, a lot of times I can have a quotient of two functions of n. So I can have f of n and g of n in the denominator. Again, I can look at my a sub n, that's my series notation, that's just the argument of this series, f of n over g of n. Okay? And if I have a quotient like this, it's a good bet that the ratio test could be a way to determine convergence or divergence. Another key that's very important before we go any further, if either of these, f or g, have factorials, that's a very good reason to use the ratio test. There's really no other test that can deal with factorials. Alright, another thing to keep in mind, which we're going to see, a sub n plus 1. What is that? All I do is anywhere I see an n in any of the functions, I just add a 1 to it. So instead of having f of n, it's going to be f of n plus 1 and g of n plus 1. Okay? Now how do I actually compute the ratio test? Well, we're going to use a variable L, that's just our limit. That's generally what's used. L is going to be the limit as n goes to infinity, and what we do is we take a sub n plus 1. We basically take the original series and just put a plus 1 after every single n, a sub n plus 1, and divide by a sub n. Okay? Now, in the context of this example, if we have a sub n plus 1, that's going to go in the numerator. That's just this, f of n plus 1 over g of n plus 1. Then we divide by a sub n. That's what we had here. Now in the denominator we have f of n over g of n. Ultimately, what that boils down to is we've got, when we put this denominator up in the numerator, we have the limit as n goes to infinity of f of n plus 1 over g of n plus 1, and then times essentially the reciprocal of the original argument. Okay, g of n over f of n. All right, that's essentially what we get. All right, and notice we've got absolute values here because we're concerned only about the absolute value. Once you get a number out of this, and you simplify and you get an answer, that's your L. If L is less than 1, the original series converges absolutely. If L is greater than 1, the series diverges. And if it's equal to 1, the test is actually inconclusive, meaning we have to pick a different test to use to actually evaluate the series. Okay? Let's actually look at an example, and hopefully this will make a little more sense. Alright, here's a good example of when to use the ratio test. We've got this series from n equals 1 to infinity of 2 to the n plus n factorial. Okay? The giveaway is the factorial. Alright? So, if we got a factorial, that's ratio test. That's pretty much just a given. Okay, so I see a factorial, we're going to use ratio test. Now remember what factorials are, because we really haven't seen a lot of those in calculus at all up to this point. A factorial means you take whatever number n is and you just multiply it successively by decreasing integer values. So if n was 6 and we had 6 factorial, that would equal 6 times 5 times 4 times 3 times 2 all the way down to times 1. So how do we compute the limit? Well, all we're going to do is we're going to use this formula up here. Okay? And you can do it any way you want. Here's one good way to think about it. Take the original argument, 2 to the n over n factorial, and just throw that reciprocal in right here. So n factorial over 2 to the n, right? Let's piece it together one step at a time. What goes on this top question mark? Well, that's going to be 2 to the n, but we have to put that plus 1 in there. So it's going to be 2 to the n plus 1, right? Notice how it's diagonal from the original 2 to the n. 2 to the n plus 1. What goes here in the denominator for n factorial? Well, it's going to be n plus 1 factorial. So this is our limit. It's the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. It takes some practice to really get where the a sub n plus 1 goes in a sub n, but once you get it, it really just boils down to, from here, simplifying this algebraically, a lot of times using exponent laws. I could have put an L equals here. So L equals the limit as n goes to infinity. This is exactly what I just had here. 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. And all I do is simplify this algebraically, all right? So, how can I simplify this 2 to the n plus 1? Well, I can use exponent laws. This should equal 2 to the n times 2 to the first, right? Because if I were to combine this back, they have the same base, so I just add the exponents, 2 to the n plus 1. So this is how I break it apart. Now, notice, this 2 to the n up here will cancel with the 1 down here. That's why it doesn't appear over here. Okay? Now, how can I simplify this factorial, n plus 1 factorial? Well, think about what n plus 1 factorial is. Well, n plus 1 factorial would be the first term, n plus 1, times the next successive term in the list, which would be what? N. So, n plus 1 factorial is the same as n plus 1 times n factorial. And the nice thing here is the n factorials cancel. Again, the main reason they don't appear over here in the next step. All right? And whenever you have these factorials here, when you evaluate the final limit, they're generally all gone. Notice here again, I don't have any factorials left. I just have the 2 remaining here, just the simple 2, and n plus 1. And now I can just straight up evaluate this limit. I could essentially think of plugging in infinity here. It would be 2 over infinity, which is 0. Okay, this is 0. So I ask myself, this limit, which is L is 0, is that less than 1 or greater than 1 or equal to 1? Well, it's definitely less than 1. So therefore, this original series from n equals 1 to infinity of 2 to the n over n factorial, this series converges absolutely by the ratio test. And that's because when I did the ratio test, L came out to be 0, which is less than 1. All right? So hopefully that made a little bit of sense. The nice thing about the ratio test is you just have to know if L is less than, it's all about 1. If it's less than 1, it converges. If it's greater than 1, it diverges. If the rare case it's equal to 1, you have to use a different test. Now, we're going to do another example of the ratio test in the next video. And after that, we're going to do one more test. Another pretty straightforward one called the root test. And in the root test, notice this box right here, those conditions. The conditions are the same for the root test. So the conditions you just learned for the ratio test are also applicable for the root test. Now the root test is mechanically a little bit different. I think it's actually easier. But these are important to remember. Okay? So hopefully the ratio test made sense here. So join us in the next video where we do another example of this. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.